So now today we're going to talk about homework 4, which we just did, and then we're going to go over the midterm review because you got a midterm on Tuesday, unless something bad happens between now and then, like a hurricane. Okay, so the first thing we're going to do is go over the homework. So I'm going to pull it up because I have a brain like a toddler. There are so many funny things that came after a toddler. Toddler on speed. Toddler on anything, really. Hasn't had his map. It's hard to say. It's a kind of chi brain.
Now I see why you weren't so perturbed about the bird conversation.
Yeah, I have, yeah. Okay, so the genes length cheap. So the first problem, should I put the homework up there? Would that be useful?
That'd be cool.
Okay. I can do that. Now we gotta wait for everything to warm up. So this first one, really I meant for you to do it the stupidest way possible, and it should be like, the whole problem should be like 11 characters. It's really cheap. Several of you did one bit or the other the long way, which is also fine. I'm in favor of doing things the harder way. Parker, I think this is the first time I've seen you without a hat on ever. And so it took me this, I was like, what the hell is wrong? Oh, right, hat. Anyway, is this up yet? Where are we at? Okay. All right, so the free fall time is the time for a sphere of uniform density to collapse to a point, ignoring everything else. So what's the cheapest way to do this? So I like this problem because you can do it really fast, and it shows you kind of an important way to be a physicist. You gotta be lazy and do things on the cheap as often as you can, because otherwise it gets intractably hard. So, or it gets really, ugly, as we saw. Where's my thing? So the first question is, write down the free fall time given just G and rho. And there are several ways to do it, and one of you, and now I'm forgetting which one of you did it in a way that I'd never seen before and I liked. But it was good. I haven't graded it. I went through everybody's homework, but I haven't assigned credit yet, because that always takes me like 4 times longer than actually reading the homework. So I haven't, homework 3 is graded and there's grades up and there's some comments on that, so that's finished. Homework 4 I will finish grading today. I will also put up all of the solution sets by the end of the day tomorrow. And if you don't see them by like 2 o'clock tomorrow, shoot me an email. Because I'm not doing it over the weekend because I don't work on the weekend. I have other stuff to do, and I'm going to forget. So I'm going to try to get everything up online, all of the homework solutions, and all of the, oh no, there aren't any slides in this. All of the videos should be up. Okay, so how do I do this? So G, rho, I need to get a time out of this. So what are the units on G? Somebody yell out one of them. There's a couple of different ways you can write it.
Meters cubed per kilogram second squared.
Meters cubed per kilogram second squared. Pretty good. I'm trying to think if there's anything else I need to say about that. There was another problem that I was going to. Okay, so I've got meters, kilograms, and second, and density. Density is in kilograms per meter cubed. So what I need to do is I need to say this thing to the A plus times this thing to the B equals what? Seconds. So the long way to do this, you can eyeball it and just see the answer if you look at it right. Or you can do it the kind of procedural way and just grind through the process and look at meters. So I've got m to the 3a, m to the minus 3b equals, I have no m's, m to the 0. That's what makes sense. And kilograms, I got kilograms to the minus a, kilograms to the plus a minus b equals kilograms again to the 0, and then seconds to the 2a equals seconds. So all I do is I just pick up all the exponents for all the units that I got, and each one is independent, so they all form their own independent equation. So now I've got 3 equations. So I've got 1, 2, 3 equations, and fortunately only 2 unknowns, which makes this an overdetermined system, which can lead to problems if your determinants aren't consistent. But we can see from this that minus 2a, pardon me, because that's on the bottom. So from this one, we see that a is minus 1/2, and from the other two, we see that a equals b. So the free fall time equals g times rho, both of those to the minus 1/2. Some of you did it with one of you had done it with Newton's law by saying that a force has got to equal g m over r squared, and that gets you a that will also get you there if you do it right. Okay, so that's the free fall time. So that's the cheap way to figure out if something's going to fall. T free fall equals 1 over g rho, square root of this. Yeah. And the second thing is can a pressure wave support a collapse before it collapses? So we need to know what the T crossing time is. If I have a blob of length L and it's got some sound speed c, then the crossing time is just L over c sound. So then the third bit is we need to say that things will collapse if T free fall is less than T cross. So we plug in and we get 1 over g rho. It's got to be less than L over c squared over c. And so the Jeans length is going to be c sound over square root of g rho. And we'll put an approximately there because there's like some 3 pi's kicking around that we weren't very careful with. But if what I want to do is ballpark whether or not this cloud is going to collapse into 1 star or 1,000,000 stars, then this is good enough. Okay, I think everybody did okay on that one. Everybody's pretty happy. Let's do, while we're on the topic of Jeans masses, let's do this let's do number 3. How did everybody feel about number 3? Pretty straightforward. Okay, so what's the Jeans mass for a cloud of molecular hydrogen gas at 10 Kelvin and 1,000 particles per cubic centimeter? This is about what a cloud of, when you see like the pillars of creation or the, what do they call them, the cliffs of creation, one of these objects is like, I'll pull this up. Oh man, no internet. How do I get an internet? Oh no, I really just get no internet. Anyway, I was going to pull up a picture of the cliffs of creation, but I can't because the internet sucks here. So anyway, you guys have all seen the pillars of creation or the Carina Nebula that JWST just released. This is one of those objects. They have a temperature of about 10 Kelvin, and they have a density of about 1,000 particles per cubic centimeter. So how do we sort out what the Jeans mass is? And let's see, did we use, so you can use, there's more than one way to write down the gene's masses, and the question is whether or not you're calling it a sphere or waving your hands around a couple of factors of pi. I'm going to use the one in the book, and I'm going to look it up because otherwise my cheap brain is not going to get all the pi's right. And it's in chapter 7, Derp. This is boring to watch. Okay, so the gene's mass, the way it is in the book, is 4/3 pi to the 5 halves. This 5 halves is the thing that is going to screw up all the time. KB B T over G times the mass, the proton to the 3 halves, times 1 over rho naught to the 1 half. Or, if you work out the details, this is about 2 solar masses times the density to the minus 1/2, and the sound speed over 0.2 kilometers per second. So I didn't show you how to get this, but if you just take if you just plug in numbers for K and G and the mass of the proton and pi, and you just work out, you just pick a value for the temperature. I wrote it as the sound speed because I like the sound speed better than the temperature. They tell you the same thing because the sound speed and the temperature are related, so we can use either one. So either one of these is fine. So the question is just we need to come up with what the sound speed is, or we can use that and get what the temperature is, and we need to sort out what the density is. Or alternatively, you could sort out what the gene's length is and say that the gene's mass is just 4/3 pi times the density times the gene's length cubed. So there's more than one way to actually get at the result. I'm going to show you this way because that's the way I did it in the solution. And so if I do it the way I did it in the solution, then I know I'm going to get the math right. Okay, so C sound is what? It's KT over M square root of that. And this is like, if you do it with this and you don't have to compute the C squared, you've got to do all the same math. Like it's all the same work in the end. I just think it's easier to think about it this way. If you plug in what this is, you get 0.2 kilometers per second. Is that how I put it up there? Oh, I called it centimeters per second because I was being kind and keeping the units consistent. This is the one that my brain remembers. You get 2 times 10 to the 5 centimeters per second. And then for the density, well, okay, this density is in grams per cubic centimeter, but I gave it to you in just per cubic centimeter because that's the units that are easier to deal with. Because otherwise you got to be dealing with like 10 to the minus 24 or 5. That's harder to keep track of versus 10 or 100. So the density in physics units, in mass units, is just going to be the mass of the particle, which I wasn't explicit about this. This is molecular hydrogen. Did I explicitly say molecular hydrogen? I did. So M is the mass of the particle, not necessarily the mass of the proton. And a particle mass here is what? It's a hydrogen molecule. So what should the mass of the hydrogen molecule be?
A proton.
Molecule.
Because diatomic hydrogen.
It's 2 protons. So the hydrogen, molecular hydrogen is 2 protons. So this is actually, and really, here's a bit that I'm not going to check if anybody did right or not. Realistically, in a molecular cloud, there's more than just hydrogen. There's also carbon monoxide and helium, and those make everything bigger. So we use 2.3 times the mass of the proton. as the mass of the particle. I used MP twice there, sorry. So the mass of the particle is 2 times the mass of the proton. That's not something that I expect anybody to know, but that's what I used for the problem. So then rho is just going to be the number density times the mass of the particle, which I got 3 times 10 to the minus 21 grams per cubic centimeter. And then you plug into that, and you get a Jean's mass of, I got 74 solar masses. So that means if I've got a blob of gas that's so big, it's going to fragment into things that are on the order of 70 some odd solar masses. Thereabouts. Okay, now I take something similar and I just heat the crap out of it. How hot did I make it in the problem? 10 to the 7? So 100 particles per cubic centimeter and 10 to the 7 Kelvin. That's pretty hot gas. This is actually kind of not a particularly realistic scenario, because generally when you get gas that's this hot, it's not as dense as 100 particles per cubic centimeter. But that's the way I wrote it wrong. So you do the same stunt, and you should get the Jean's mass of this should be like, I think I got 10 to the 11 solar masses. How much is a solar mass? It's 2 times 10 to the 30 kilograms. So some of you got numbers that were like 10 to the 45. It's totally fine as long as your units were there. If your units were missing, I'm going to assume that you mean kilograms. Maybe I'll assume that you mean solar masses, and then everybody gets it wrong. I think everybody's generally pretty consistent with units. Is everybody good with number 3? Does anybody have any approximations they made that they want to talk about? All right, let's do the other 2. Let's do number 5 first. Or 4.
I didn't know how long it took.
Okay, how long did it take everybody? That continues to be useful for whether or not the problem was way too hard or not. For me, anyway. Okay, so number 5, 5.5 out of the book said start with a particular formulation of the Euler of the Navier-Stokes equation and show that it looks like something else. So it says start with rho dvi dt equals
Negative T.
minus d pi I j dx j. Is that right? That's how they said it.
It's PIJ, not pi.
Oh yeah, it was a big P.
Yes.
Pij. And then Pij is the isotropic pressure. That's just the gas pressure times delta Ij. I know it's isotropic because it's a scalar. This is a tensor. It has directional information. But the pressure part is a scalar. It doesn't care about the direction. This part says delta Ij just makes everything look the same. Makes I equal to j. Plus some other pi Ij, whatever that happens to be. And you can do the problem without caring what that is. It's just some other pressure tensor, whatever it is. And it's a tensor, so the pressure in one direction is going to be maybe different from the pressure in another direction. But that's okay. I don't care about that. This is just extra stuff. Now, in reality, this turns into nu times dx dvi dxj, and we get a minus sign in front of that. So this is the approximation that we make. So now I'm going a little tangentially. This is the approximation that we're going to make. And then this isn't general enough. We need to make this isotropic. So to make this isotropic, we say, okay, that is actually equal to 1/2 this and its opposite, and then we take off some other stuff. So we do a little bit of crap with this to make it look like the last part of the book. We'll talk about that in a second. that's where we're going. But we can forget about the form of pi for a second. And so what it wants you to what it wants you to show is that 1/2 the time derivative of 1/2 rho v squared is equal to what? Minus div of rho v 1/2 v squared plus p over rho plus rho pi ij. All that business is inside the div plus pi ij vi dxj. I happen to remember how that all works, but let me double check that I didn't screw anything up. Yeah, that's all right. So this is where we're going. But we got to start with here. And that's where we're going. Here's where we're starting. So why is it 1/2 mv squared?
Is it the kinetic energy per unit mass? So
Well, just in general, why 1/2? Well, because I need an energy, and I know that work is energy, right? Work and energy are related. What's work? Work is dx dot f. That's work. Power is dv times f. So the rate of doing work is v dot f. That's the rate of changing energy, right? Everybody on board with that? So what is that? This is just v dot m dv dt. But this, I can just integrate this. I can just pull this v inside the integral, and I get 1/2 m dv squared dt. Right? Or I pull the mass into the derivative as well, because if I'm doing this properly, the mass ought to be inside the derivative. I get d by dt of 1/2 mv squared. So the 1/2 comes from the fact that you're dotting velocity into its derivative, and then you integrate. So that's where that 1/2 comes from. And that's exactly what we're doing here. So we're going to take this equation. So there's two ways to think about how you're approaching this. So you can either start with this equation and dot velocity into it and then do a bunch of calculus. Or I can start with the question that I'm asking, what is this? And expand that with chain rule, and you'll see that it's actually, you're doing the same thing. So there's just different ways to conceptually think about this. So I find it easier to start with the question that you're asking. So if I start with this, and I take a partial derivative of this, the partial derivative of the left-hand side is going to be 1/2 v squared d rho dt plus rho v dv dt. Now, that's the whole derivative. We're going to throw this one out because what does the problem say about the assumption? It isn't up there. I can put it up there.
incompressible.
Incompressible. So what does incompressible mean? Incompressible means that d rho dt is 0. Incompressible also means that div v is 0. Why? Because d rho dt, the full derivative, is equal to minus rho div v. So if this is 0, so is div v. So those two things are 0 together. So I get to use both of those, and I will. So rho v dot partial v partial t. Well, it said use this equation, but I've got a partial. So let's expand this out. So this turns into rho times partial v partial t plus v dot grad v. That's that. Equals minus dpij dxj. So let's punt that guy over to the other side, and we get rho dv dt equals minus dpij dxj minus rho v dot rad b. Let's be explicit with these indices. Rho vj dj bi. Now pay attention to the indices. I may screw it up. If I do, holler. Okay, so this looks like this. That's what we're looking for. So we'll just dot velocity into this equation, and we're left with rho vi. This is because I'm dotting. This is vi now. The dot product means that I'm going to add a vi. My vector index is vi, so I'm going to add another vi. dvi dt equals minus vi d by dj of pij minus rho vj dj vi. And on the switchboard. No. Still need that. I want this guy still. Go over here. Yeah.
Where does the VI go in that term?
I missed it. Because I need a VI on everybody. Thank you. Okay, so now the stunt is just integrate by parts and then throw out all the div v terms. So A to B plus B to A is DAB, or A to B, where little d is whatever differential operator I feel like sticking in there. It could be nabla, it could be the time derivative, it could be one space derivative, it could be all kinds of things. As long as A and B aren't tensors or something weird. DAB minus DA. So you could think about it as thing times a derivative is equal to the derivative of both things minus derivative times the derivative of thing minus the reverse. So so now we're just going to do this a couple of times on here. So the left-hand side is what I'm looking for. That's 1/2 rho v squared. So let's start with this term here. Yeah, let's start with the second term. So we start off, we've got rho dvi dt equals minus vi dj pij minus rho vi vj dj vi. Now it's super important to keep your i's and j's clear. Not a dot, left or right. So this guy, let's get rid of this. So the whole purpose, what are we doing? Let's take an aside for a second. How do I know where to go? How do I know what to integrate by parts? So what I'm going to try to do is I have partial of thing, and I want to rewrite this as d by dt of a thing plus div of a flux equals 0. Let's make this a real letter. Let's call this Q. Whatever Q is. Q will be 1/2 rho v squared, but Q could be total energy, Q could be density, Q could be any conserved quantity. Any quantity that's conserved, you can write it down like this. And what this says as an equation, if I integrate over volume, then what this equation says is in some region of space, the total change in Q is the flux across the surface, wherever the flux happens to be. And the flux for density is just rho v. For momentum, it's rho v plus p. So it's just moving the momentum plus whatever acceleration. But they're all still conserved quantities. So what we're going to do is we're going to try to do this. We're going to try to rewrite this equation here as d rho dt, which is how we started, equals minus grad of a bunch of stuff. But I don't have grad of a bunch of stuff. What I have is minus v times grad stuff. So I got to get that v on the inside so that I have a grad. So let's start with this last term. And I'm going to, the net result looks like I'm doing something that I'm not. I'll show you in a second. So we integrate this by parts. What I want is, so I've got what I want is dj of rho vi dj vi. Now I get a 1/2 because I'm packing this vj across the j. So when I integrate, I get a 1/2. And then I'm left with the other side. Actually, let's do it. Actually, sorry, let's start with this term first, because this term is going to be useful, easier to deal with. So we start with vi dj pij. I invert this, and this turns into dj vi pij minus pij dj vi. That make sense? So this first term, let's expand out what pij is. This is dj times vj times p plus p delta ij plus pi ij. Good. And then I'm left with p delta ij plus pi ij dvi dxj. So now these all are things that I'm looking for. They're all inside a div, so we'll hang on to these. Let's look at these. This one I can't get rid of yet. Also, if you look at the problem, this is the thing that I'm looking for. But this p delta ij, where does it go? Why does it go away? I'm gonna kill it. Ow. Let's just write it by itself. P delta ij dvi dxj. So now I'm summing over all 4 indices because I've got 2 repeated indices. So there's actually 9 terms that I just wrote down because I've got 2 repeated indices. So they all repeat. But what does this delta ij do? Yeah, say that out loud louder.
I equals j.
So it just makes I equal to j because it kills everything else in the term. So I've got these 9 terms. 6 of them get killed, and I'm just left with I equals j. So this term just becomes p dvi dxi. And what's that? What is dvi dxi? Yeah, why is it 0? Because it's incompressible. Because dvi dxi is div v. And because it's incompressible, because what I said over there, this term is 0, so this term goes away. So I'm left with, let's write over here, d by dt of 1/2 rho v squared. That's where I started. And now I've got d by dj of, I've got vj times pressure delta ij. This delta is missing from the book. I hope that didn't confuse anybody too hard. There ought to be a delta in the problem, but there isn't. It's just a p. Plus pi ij plus Now there's other stuff that's going to go in there, plus pi ij dvi dxj. So that's the other term that I got. And then that guy disappeared. So then we need to deal with this last term. And what is it that we need this to turn into? This needs to look like a 1/2 rho v squared vj, because we'll have a d by dj. And you can see that I'm going to have all three of those when I bring them inside. So I have these, and they go, and I integrate by parts again, and they go inside. Does that make sense? So I'm just going to integrate this by parts again, and I get a 1/2 rho v squared minus, let's see, why does that term disappear? Did I do something wrong? Oh, yeah. Vi times dj vj times rho vi. But the divergence term is 0. That's dj vj. So that goes away too. So then we're left with just d by dt of 1/2 rho v squared, that's what we started with, is equal to minus div rho v times 1/2 v squared plus, I'm just going to write it out the way I like to write it. Rho v times 1/2 v squared plus v times p. Now this needs a j, this needs a j, this needs a j, plus vj pi ij plus pi ij dvi dxj. Okay, so what do we got? We've got, now we have dq, that's this stuff in here, plus div f, that's all this stuff, equals stuff, pi ij dvi dxj. So this is the loss. So this side says that Q is conserved and it's pushed around like F. And then the other term that I can't get into that grad term is the dissipation. So if I take some kind of volume, say I've got some box with gas in it, or a bottle, and I'm stirring the bottle. I stir the bottle up, I stir the water in the bottle up, and then I let it decay. If I integrate this over space, the only thing I'm left with is this term. I'm left with the time derivative is equal to just this term here, which is equal to, if we plug in what we know for pi ij is equal to minus mu times dvi dxj. But that's not really symmetric enough, so we rewrite this as minus mu times 1/2 dvi dxj plus dvj dxi. Now I have something that's isotropic but still has the same behavior as the other one. And I've got two of those, so really I just have a square on that. So my dissipation rate, dvi dxj times this, is just going to be the viscosity times 1/2 of the gradient term squared. So when you stir cream, do you guys take your coffee with cream? Do you take it black? So when you stir your pollutant into your coffee, you make some large-scale motion, and that cascades down to smaller motion. We haven't talked about that yet. We will, don't you worry. And then at the very smallest scale, it gets dissipated by little tiny tubes of vorticity, just like this. And then that energy turns into heat. But this is how it does it. Wait, does anybody have any questions about this problem? or any of the steps in this problem, everybody feel like they could do this one if I gave it to them on the midterm? Maybe it's a little long. This is probably longer than I would give you on the midterm, but I haven't written the midterm yet, so I haven't decided. Like it might be the only thing that I give you. But this is probably harder than what I would give you on a midterm. The final is longer. Okay, and the last problem, number 7. There's nothing up there. I do, however, have to go through the book for this one because otherwise I will mess it up. Some things I can remember, and some things I horse up. Okay, so what the problem says is now we have, so we start off with our two fluid interface, and we've got rho prime u prime at the top and rho u at the bottom. But now we want to incorporate surface tension because water has surface tension and it's actually very important. You guys ever go into the woods and look at the bugs that swim around like on the top of the water? They're kind of magnificent. Like they live their entire life just sitting on top of water. How do they do that? They do that with surface tension. So they're light enough that they're buoyant just based on the surface tension. So what is surface tension? If I have a little bit of curvature, then these molecules over here start to hang on to each other pretty tight because of the cohesive force between the molecules in the water. So they're going to hang on to each other, and you're going to get a little extra tension. And it's going to go like the curvature. It's going to go like the second derivative of the surface. So that goes like minus t times d squared c dx squared. And this behaves like a pressure. We're a force per unit volume, which is pressure. Pressure is just, well, no, pressure is an energy per unit volume. This is like a force. So this turns into a force like the pressure. So you go through okay, so what we do, we say that B is minus grad phi. We have some potential flow. We go through a little bit of algebra and we get an evolution equation for phi, which goes like minus phi plus 1/2 v squared equals minus p minus the gravitational potential. Right? So this is again just Navier-Stokes or Euler's equation. But what we did was we used the fact that we can call it potential flow, and we just made everything looks like a gradient if it's incompressible. So then we can write this beautiful equation. Missing a row. Now I'm good. Okay, so then we need to talk about the interface. C is the height of the interface. dc dt equals the velocity in the vertical component, which is equal to d phi dz. It's also equal to partial c partial t plus u partial c partial x. So we need that. And what else do we need? Then we're going to say that the perturbation is going to go like a e to the I k x minus omega t. And then my potentials, phi, is going to go like c e to the I kx minus omega t. Phi is on the bottom. I want it to go to 0 at infinity. So this is something times z. It's either k, it's k times z, and it's either a plus or a minus. This is phi, it's the bottom, so z goes to minus infinity, so this needs to be a plus. Did you follow that? So then phi prime, which is the top, is going to be c prime e to the I kx minus omega t minus kg. All right. Then, so these are the tools that we're going to need. Then we solve this for P, and we say that pressure equals constant. So that gives us a minus d phi dt. Let's see, I'm going to read it like the book does. So I'm just going to skip to 745. We are left with rho times minus d phi dt minus u d phi dx plus gc1 equals rho prime minus d phi prime dt minus u prime d phi prime dx plus gc1. And then, but now I need to actually have something else here. So now I need to add in this plus t d psi dx squared on the bottom term. The top term doesn't have any surface tension, or if it does, you got to deal with that separately. So we'll add this plus t d c dx squared. Does that jive with what everybody did?
Professor?
Yeah.
Can you explain that?
This bit?
Yeah.
Yeah, so what I do here is so this is equal to the pressure in the bottom. No, sorry, pressure in the, whoa, lies. That is not what you did. You put it on the bottom part because the bottom has the bottom fluid has the pressure. So plus t d squared c dx squared. So all I'm doing is adding this here on the bottom equation. So when I solve it for pressure, I also get this t d c dx squared. But that only happens at the bottom one. So my bottom equation is, so this is the pressure, and then I'm adding this guy here. And then the top one, I don't add any other pressure. Does that make sense? Now, we drop in our of our Fourier modes. And what are we left with? Rho is constant, so it's not in both sides, so it's not going to change. That's a very handy thing. So I'm not going to worry about that one. But this one, d phi dt, so I get a rho. d phi dt gives me a minus I omega times phi gets c. And then I get a minus u, and then I get a d phi dx, and that gets c times a k. So let's simplify this whole term. So both of these guys are minus omega plus k times u times c. So I get an omega, a k, a u, and a c. That's from these two things. Plus g times a, that's from c. And then each one of these also has an e to the I kx minus omega t, but we're going to get rid of it. We're just going to divide up through by all of them. This one has an I kx minus omega t minus kz, but we're going to set k equal to 0 because the only place that the pressure matches
Z equals 0. Not
z equals 0, not k equals 0. Thank you. We're going to set z equals 0 because the only place that the pressure matches is at z equals 0. If I set k equal to 0, then I have constant waves. K equals 0 is the constant wave. That's a boring wave. So those guys are going to disappear, and I'm left just with this. So I've got a rho times omega u c g a plus t times k squared c, but that c just gives me an a. Because the, I think I get a minus there. I feel like this is a minus sign that I might screw up later. So get a minus k squared from that second derivative. So now I have a page of algebra to do. I've got to plug in, let's see, what else do I know from, where are my other equations? Here. Is this from last week? This is from last week. But I'm going to stick with it. So we have these guys from these equations. So from the motion of the interface, you get equations that look like that. And between this one and that one, you just got to do a bunch of algebra, which I'm not going to do because it's super boring to watch. Unless anybody really had some trouble with this algebra that they really want to see. But it just gets sucked onto the A. So anywhere the G shows up, you're going to get a T times K squared A as well. So your final dispersion relationship after the algebra all settles says omega over K equals rho U plus rho prime U prime over rho plus rho prime plus or minus square root of G over K times everybody, rho minus rho prime over rho plus rho prime, plus the new thing, K squared T over rho plus rho prime, minus rho prime U minus U prime squared over rho plus rho prime squared 1/2. Okay, ugly, long, but we'll simplify it. We'll do some stuff with it first. So we'll hang on to that. Let's shove that over there. Okay, so what does the book say? So what is the phase velocity of surface waves on the air-water interface? Show that the velocity is minimum for a particular wavelength. Given t equals 74 dynes per centimeter, calculate this wavelength. Okay, so we're talking about an air-water interface, so I think it's fair to just say that the velocity is 0. We're just talking about the surface wave of my infinitely deep ocean. So omega over k equals, that first term disappears, the last term disappears, plus or minus g over k times rho plus rho minus rho prime over rho plus rho prime plus k squared t over rho plus rho prime. Okay, so first, what is the phase velocity? That is the phase velocity. I have written that. So that is dp equals that. Second, show that it's a minimum. So how do you find out if something's a minimum?
Derivative 0.
Derivative's got to be 0. So I take the derivative of this business.
You had to rewrite it in terms of the wavelength first,
I do.
which is 2 pi over k.
Which is, what's that?
2 pi over k, right?
Yeah, I can just do it with k and then invert there. Is it easier to do it with the wavelength? All right. Omega times, so if we say that k equals 2 pi, or, yeah, k equals 2 pi over L, yeah? Then this is omega times L over 2 pi equals plus or minus L times G times delta rho over average rho. I'm going to shorthand that. Plus T over average rho times L squared. I divide through by an L, and I get omega over 2 pi equals plus or minus. If I screw something up, please holler. Because this is not one that I remember exactly. Equals 1/2 LG delta rho over average rho plus T over average rho all squared over G delta rho over average rho plus T over the derivative at the bottom. Yeah. This is why I skipped the calculus most people. Does anybody have this derivative off the top of their head?
Well, I made the assumption that P is much greater than P prime.
Thank you. I knew there was something that I was missing. So what did you make? The assumption that you made
P
was
is much greater than P prime. So
there's no p's up there. Rho.
Rows.
Rho is much greater than rho prime. So how does that simplify things? Sorry, I knew there was something else.
G over K.
So okay, that makes life simpler. So if we assume that rho is much larger than rho prime, we just say rho prime is 0, and this simplifies to plus or minus G over K, and that's just 1 now. Plus K squared T, and then that's just rho, we can call that 1, right?
Yeah, and then when you do your derivative and set it equal to 0, you get lambda, or length equals 2 pi times the root of T over GP, or G rho.
What'd you get?
2 pi times root of T over G rho.
Rho T over G rho?
Then root
Oh,
of
root of
T over G rho.
G rho. Thank you.
G rho is included in the root.
Thanks. All right, I will check this up, and there will be a good solution shortly. Okay, so you get some. So you get a wavelength. That is the easier way to do it. Thank you. So you get a wavelength that's the minimum of this, and I think everybody got something that was like 0.5 centimeter, a couple of centimeters. 1.7. That's like half. It's not 7. It's not a kilometer.
1.7 centimeters.
Was that? You said 1.7?
Yeah.
I'm only out by a factor of 3. That's pretty close. There's a spread of answers that people got depending on what you assume for rho. But you get on the order of about a centimeter.
Rho is roughly 1?
Rho is 1, so.
Or 1.025 for salt water?
Yeah, you can call it 1.
Salt water.
You didn't say anything about salt water in the ocean.
Yeah, but he didn't assume an ocean. But lakes, the Great Lakes are not salty, and they're enormous.
But not nearly the size of the ocean.
That's really true. This approximation actually breaks down for the Great Lakes because they're not very deep. I mean, Lake Superior is actually crazy deep. But anyway, does anybody have any other questions on that one? And then the last one, what did the last one say? The last one said, what's the minimum amount you have to blow to get things to get wet with this temperature? And now, so the question says, what is the critical value of rho minus, or u minus u prime for things to become unstable? So actually solving anything with a non-trivial u and u prime with this whole monster is kind of horrible, but you don't need to do that. You only need to do when this is going to be imaginary. So you just need to know when this thing blows up. This thing is going to be well behaved. This one will blow up though. So we just need to sort out when this is going to be negative. So we have G over K. Here, they set an air-water interface. Here you can't set rho prime to 0 or it doesn't work. Because then you're blowing with nothing. That doesn't make any sense. So you can't send rho prime to 0, but you can send it to something small, but then you got to do a Taylor expansion, which I don't feel like doing. G over K times rho, delta rho over average rho, plus K squared T over average rho, minus rho prime, u minus u prime, over rho plus rho prime squared. Now all of this goes into the square root, but I don't care about that. I just need it to be less than 0. Because the square root doesn't change the sign. So we'll take this gnarly thing and we'll just extract the part that I care about. the part that's doing stuff is this, so then we just solve for u minus u prime, and you get u minus u prime has got to be greater than, because there's a minus sign there, g over k times delta rho over average rho plus k squared t over average rho times rho plus rho prime squared over rho prime.
The root of that.
And I squared that. So this is how hard you have to blow. And this is nice because even without surface tension, you can see that there's a non-trivial smallest velocity that you have to blow to get it out of the water. That might be a fun project to do, to see how hard you actually have to blow to make things wet. Okay, so that is the homework. Oh, and that is our time, because it's now 2:30. We were done at 2:35, right?
Yeah.
Okay. I was going to go through midterm review, but the midterm review is basically what I just did. So if you followed all of that, you'll be fine on the midterm. But let me tell you a couple of things first before we go. So, that will be on the test. So make sure you know where these equations come from. One of the reasons that I like this class, one of the reasons that I like this field is because you can just start with some assumptions and then turn them into math without too much pain. Doing this with E&M is hard. Doing it with quantum mechanics is actually not super hard, but you don't ever do that. Nobody ever shows you the derivation, but you can see where Navier-Stokes and continuity come from. So make sure that you can do that. I don't feel bad asking you to derive Navier-Stokes on the test because it's not too bad. It's only a couple of lines once you know what you're doing. The book does it in a very elaborate way, talks about a lot of stuff. The important bit with the derivative term is nu dvx dx is the surface, is the force on the surface. Then when I turn that into a body integral, I get another derivative. And so that's why that looks like nu d squared dx squared. Did you follow that? When I'm talking about continuity, I have, I get something that looks like d rho dt, the integral over volume, equals the integral of minus rho v on the surface. And then because this is a surface integral, I turn this into a volume integral, equals minus integral of div rho v dv. And so that's where continuity comes from. You should say a little bit more than what I just did, but that's really all I'm looking for. When I do the same thing with the force term, it turns into the grad squared term. So that's where the Navier-Stokes comes from. So that's thing one that I want to make sure that everybody has on their radar. Let's see. Pulling up my list of stuff. Here's what we did. This is what we did. All right. There's a good list of everything that I think that we did on that video that is here. Let's see. So we did a lot of turning things into conservative form. Things like that. So we did it with the total energy, we did it with the momentum. I'm not going to ask you anything that's going to take you longer than like 10 minutes to derive. But make sure that you understand how those derivations go. We did a lot of linearization and stability. make sure you understand how those processes all go, how to linearize something, how to look at the stability of it. I wouldn't feel bad coming up with some goofy ass equation and asking you to linearize it and tell me when it's stable or not. That isn't hydro. I wouldn't feel bad asking you to do some fraction of the sound wave derivation. It is a little long, but it's not super painful. What else did we talk about? We talked about shear flow or pipe flow. We did a couple of problems on that. We talked a lot about waves. And then we talked a lot about various instabilities. And we talked about Reynolds numbers. So for the first half, we kind of throw out the nonlinear term for almost everything, unless we have to. But the Reynolds number is what tells us when we have to keep the nonlinear term. When we get back from the midterm, we're going to talk about the nonlinear term more, but we're actually not going to talk about. We're going to talk about turbulence. But it's the nonlinear term that makes the turbulence happen. Okay, those are the kind of key things. That's not an exhaustive list. But if it's on the homeworks and isn't one of those things that took you 3 hours, it's fair game. You should make sure you understand the ones that took you 3 hours too, because I like those ideas and I might move to those ideas. Yeah.
Do we need a calculator?
Oh, probably bring one just in case. I don't really like numbers, so I usually don't have numbers, but they do make good problems. So, was that?
Numbers are great. Number theory.
Yeah, I get bored by numbers. I like shapes and relationships.
Numbers and shapes are the same thing.
No, numbers are putting something specific on it. You don't need numbers to talk about relationships and shapes. I don't care what units anybody's in.
You can connect the monster group to the monster group? Yeah, it's a number theory to like abstract geometries.
Oh, sure. There's lots of things. It's just the thing is, I hate units, and numbers all have units.
The